Oh, I can't hear anything. Hello?
Oh, sorry. You can hear me now. Sorry.
Yeah, yeah.
Yeah, I didn't say anything. Just I
Okay,
said
okay.
conditional.
Okay.
So rho x belongs to d of h, x belonging to x. So we have this px belong to d. When I say d of x, I mean it's just a distribution on x. It's a PMF. Rho x, we just rewrote kind of the spectral decomposition as q y given x, y given x, e y, just the notation, y belonging to y. Okay, this is d of h. Okay, we defined the t delta. So let's say rho xn delta. I mean, I had a different notation there. I just put the span of the so E yn given xn. So what do I mean by this? This I mean I equal to 1 through n ey I given xi. This is also the same as just writing it in EYN given xn, such that xn and yn, when put together, this is in the classical typicality of qy given x. This is what it is. And then we had pi rho xn. If you want to put the delta. So this is summation yn such that xn yn I will belongs to t delta n px qy given x of the rank 1 projector I equal to 1 through n EYI given xi. This is just a notation. EYI given xi.
Sir, hello. Hello.
Yeah.
Sir, in the last session, you said like it belongs to T2 delta, and like, does it make difference or like?
No, I think yeah, I'll be clear. I think what so this definition, maybe let me see. No, oh, okay. So thank you for pointing that out. I will say this is delta itself. Okay, I will.
Yes. Okay.
I will write this as delta. Thank you. See, what I wish to say is the following. Okay, why did the 2 delta come? What was in my mind is the following. So I'll tell you the proposition and then it will make sense. So proposition. Suppose xn belong to t delta npx, the classical typicality. Then there exists n delta. Obviously, it depends on this collection of rows, right? Row x, I'll just put x belonging to x. So this n depends on the entire collection. There exists this, and an alpha. I will explain all this. Alpha that depends on delta and this collection rho x. greater than equal to 0 such that 1 such that for all n greater than equal to n delta this thing, trace the overlap between pi rho xn. So this is where I meant the true delta. So the true delta comes here. Rho xn is greater than equal to 1 minus alpha, e power exp minus n times alpha delta, and this collection. What I'm just saying is that this exponent depends on the entire collection. That's all I'm saying. 2, we have the following, right? Dimension of this conditional typical subspace. So T rho xn delta, which is also equal to the trace of the projector on projector rho xn delta. You can write delta here. That's fine. It's delta here. This is less than equal to and lower than greater than or equal to. So what is these expressions? I suggested you to guess, but I'll just write it again. I mean, I'm going to write it and then again poll for what your guesses are. Exp n times something here plus delta plus let me put 3 delta just for correctness. And here I have 1 minus exp minus n times alpha, that same alpha, I'm not going to write it subscripts, exp n times something here minus 3 delta. Okay, I'll fill that up. 3 3 we have pi rho xn. Let me put 2 delta here. Rho xn. I'm thinking this should also be 2 delta. I have to double check this calculation whether it is 2 delta or just a red star here. Is it correct? Instead of a star, we'll write the question. Okay. Pi rho xn 2 delta. This is 2 power minus n times something minus 3 delta pi rho xn 2 delta. Sorry, pi rho xn 2 delta, and it dominates 2 power minus n times something minus 3 delta pi rho xn, operator dominance. Okay. So the question is, what is this? Okay. I will wait for you to think and tell me. I mean, I'll poll for each one of you. So let me show this whole thing. For a minute. Also try and switch on the video. What is this? Okay. Okay. So what is this? Tejas, any guess?
Like, I think it would be S of rho n and then something.
Rho
Like
n?
normally,
go back to the classical. That's why I tried to do the classical very carefully.
classical we would have h of y given x.
Okay.
So the y here is sort of the sequence. So classically, we first found out the
What
joint
is this?
distribution of
What
x
is
and
this? What is this? What is this? Okay, I have given you too much. I've given all of you too much clue. So now, all of you
what
think it.
oh, you mean what is that in the quantum thing?
No, in the classical thing.
Oh, h of x comma y minus h of x.
Okay, is there a different expression?
For mutual information, I of no, sorry.
Hello.
Yeah.
So, I mean, when we did the exercise, like the first exercise, it was classical entropy. So, h of
Yeah.
px, h of x. So, this by the pattern, I think this could be s of p something. I mean, s of rho x.
Yeah. What is this? What is it?
What is means? Are you asking for the exact expression?
Yeah, yeah. This is a very simple thing.
Or it will be like summation of h of y given x
Oh,
times p of x.
Uh-huh.
So
y
here
given, y given.
x equal to some small x, the whole thing times p of x. So now in this setting,
Quantize it.
oh yeah, okay. So h of y given x equal to x would just be s of rho x.
Uh-huh.
And then there you would have, yeah, you already have a p of x. I think,
It's going to be this.
yeah, correct.
That's it. I'll write it better here. Does it make sense? See, the same quantities I told you that, I mean, in the class I told you that rho x kind of corresponds to the PMF Py given x, y belonging to y, right? This is what I told you. Now, if you look at that, right, you essentially get an average of these conditional entropies. In the classical case, this is what you get. You get the entropy of this distribution Py given x of y given x. You take this probability mass function and you look at its entropy and then you average it over Px. So you should expect exactly the same thing. So you're going to get something like this, right? Px of x, s of rho x. That's exactly what we get. Make sense?
Yeah.
Yeah. Srinidhi, is it okay? Saptarishi, is it okay?
Yes, sir.
You might want, Saptarishi might
Yes,
want
sir.
to revisit the link. Yeah. Okay. So, so this is your conditional quantum typicality. Okay, again, the proofs are identical. Okay, if you let's try the first one. Remember, I told you that you should always do this first one and then the second one and then the third one. I remember in the first one itself you had trouble last time, right? In the I think this is what Srinidhi also mentioned at the end of the last class. So the proof of the first part. If you do the first part proof, the second part proof is straightforward, and the one of the things in the third part is not difficult. So yeah, so let me indicate, actually the proof of the first part also boils down to the proof of the classical conditional typicality, the hard question. Okay, so let me indicate. So proof. So what are we doing? So we are given this, right? Row X is essentially Qy given X of Y given X, Ey given X, Ey given X, right? Actually, I mean, it's trivial really. So you have the sequence x1 through xn. So the quantum state is what? The quantum state is the following. So if I look at row xn, which is by definition row x1 tensor, row x2 all the way tensor until row xn. If I look at this is the following. Yn belonging to Yn, product, I'm just writing it explicitly, I equal to 1 through n, q y given x of yi given xi, right? These x1 through xn's are fixed. You're summing over all the yns. E y1 given x1 tensor all the way. See, you have to be careful. The notation, you might just wondering, okay, what's going on? I'm just writing the same thing in the classical. It's not, because of the non-commutativity. So the notation should be both good to enable you recognize the similarity, but at the same time you have to caution about the differences. Okay, so this is your row xn. What is pi rho delta n? Pi rho xn delta. This is, I'll just write Zn. Zn belonging to 2t2 delta n. Sorry, this is a 2 here. So pxqy given x. If you observe, this is our notation in the homework. What will it be here? It will be e z1 given x1 all the way until e zn given xn, e z1 given x1 all the way until e zn given xn. See, the xn's are fixed, okay? x1, x2, xn are all fixed. So when I do pi rho xn 2 delta times rho xn, what do I get? I have to do a product of these two folks. So I'm going to copy, paste, and what I will do, the scalar can move. I can pull the sum together. So I have something like this. This, yeah, I am not interchanging the operator. Yeah, to be careful. The operator should not get interchanged. So this has to come to the right. Okay, this is what it is. Because I've used z for pi and y for rho. Okay, so this is what it is. Now remember, I told you this. So the x1s are all same. Okay, so this x1 is same as this x1. This xn is same as this xn. So, and remember I told you that e y given x inner product with e z given x equal to delta yz. So which means the summation will squish. I mean, the second summation will be only running on those where the Zn is equal to Yn. So you end up getting, because of the previous, the red thing, you end up getting, this is a smaller sum. The Zn sum is a smaller sum. So only those terms will survive. And I am going to write it this way. So what I'll do is I'll actually, okay, so what I'll do is I'll actually, just for clarity, I'm going to write this whole thing, copy, paste, and I will say instead of this whole inner product, I am going to write this as delta Z1 Y1, delta Z2 Y2, all the way until delta Z and Yn. So that means, so that squishes the, okay, so I'm going to get this thing here, hopefully, yeah. So that squishes the summation, and I will have only one summation. So Zn T2 2 delta n Px Qy given x of xn. Okay, I'll have the same. So now y equal to z. So this product, so I will have q y given x of zi given xi, because the yi is equal to xi, and I just have e z1 given x1 all the way until e zn given xn, outer product e z1 given x1 all the way until e zn given xn. And I have just computed the operator, and now I have to do the trace. So when I do the trace, so I do the trace of this object, the outer product switches as an inner product, paste. So the outer product switches as an inner product, and I will have exactly what I had in the classical case, 2T2 delta n Px Q y given x of xn, product I equal to 1 through n Q y given x of zi given xi. I have this. So, and this by the homework, I mean, which I think Srinidhi asked, I'll show it in a discussion session. So 1 minus exp minus n times alpha, something that depends on a bunch of terms. So you can see how it essentially boils down to that. So the rest of the proofs are also similar, but I will give this as a homework, and I will also kind of do it. I mean, once you submit it, I'll do it. It's not, this homework will be much easier once you looked at the previous homework, but just, just this kind of a reduction to the classical case is important. I will just keep this like this for a minute and then move on, and then ask for questions, and then I won't do the rest of the proofs. That will be the homework, but then I'll go to the next thing, which is more interesting.
Sir, like, what is the significance of using 2 delta here?
See, that comes from your so that will be answered if you solve this. So and Srinidhi, we'll do it tomorrow. So remember, if xn, I told you, if xn belongs to t delta npx, then you can only show this. I mean, I had given this in the homework, and there is a 2 delta here, if you recall.
Yes, sir.
Yeah, and the reason is, see, there is a triangular inequality that comes. When we do this tomorrow, your question will be solved. If some of you who has already solved this will be able to appreciate that. But if you are having a question, this will get solved tomorrow.
Okay, sir.
So it's something like this. Yeah, okay, so let me tell you, let me indicate to you why it comes. I mean, not why it comes, but what is the issue. So you can show this is greater than 1 minus epsilon, 1 minus, exp minus n times alpha. Okay. If you take this to be delta, you cannot show this. It need not be 2 delta, but it has to be some delta plus some delta prime, where delta prime has to be greater than 0. You cannot do it without that. The thing is, there is this delta prime is for another concentration that is coming in. Remember, you cannot show, so you cannot, so xn belongs to 2t delta npx. Px of n of xn, this you can show is greater than or equal to 1 minus exp minus n alpha only if delta is positive, right? You can't show if delta equal to 0. Similarly,
Yeah.
this delta prime comes as another concentration term here. There are two concentration. I mean, there's only one concentration, but this delta is embedded and this delta prime comes. So we'll see it. We'll see it when we solve that problem. That problem which you know you are unable to do in the homework. You will see that.
Okay.
Okay. If this is okay, I will then start to motivate, start to go towards the. Just for reference from the book, right? This is 15.2.3 as I told you, and this is particularly what I have covered is 15.2.4. Property 15.2.4, property 15.2.5, and property 15.2.6 in Wild, and yeah, he gives the proofs later on, and his anyway. You can't take. I mean, you can't take this proof because my definition of quantum typicality, strong conditional quantum typicality is slightly different from his definition. But anyway, you'll get the idea. So this is 15.2.4, 2.5, and 2.6 from the book. Okay, so now I will start to go towards packing lemma, but I'll do it slightly differently. I'll do it differently from what he does it. Okay, packing lemma. I'll go towards packing lemma. Now I'll kind of motivate what's going on. I'll motivate a problem, and I'll motivate a problem and then indicate how this comes as an important tool in not just that problem but many other scenarios. Okay, so this alludes back to your previous to what I explained in the previous class. So I will do it again. So think of yourself, as I said, exactly the same. I'm going to draw exactly the same figure. So you have a machine. It has a lever, and it can be placed either in the up position or the down position. And if it's placed in the up position, you will get a. If you place the lever in the up position, that is 0, you will get a particular quantum state whose characterization is rho 0. If you place the lever in the down position, you will design another quantum state whose characterization is rho 1. Okay. So we are it will prepare that quantum state and throw it out. Now, so the idea is to use quantum states as information carriers. So I'll give you the setting. So I will describe the problem, and it will be very similar to what I've described to you informally for some of you, but I'll do it formally here. So so you're going to use these prepared quantum states as essentially information carriers. Okay. So you have I'll state the setting. So every so information rate is, say, r bits per second. So that means every second you are getting r bits. Let's take, throughout I'll kind of go through an example and you will understand. So I'll say r equal to, say, 1/3. So that means every 3 seconds you are getting a bit, an information bit. So that information bit means it can be either 0 or 1, equally likely. Okay. So Alice is here. she has this machine with her. She's getting these information bits with equal likely, and she's going to keep moving the lever, and she's going to generate a bunch of particles. The machine is going to prepare a bunch of particles according to where she places her levers, and this thing will go through a noiseless qubit pipe. Okay, noiseless qubit pipe. And so these very particles are received by Bob, and Bob has to do a measurement on this. And try and read out the bits that Alice encoded in that quantum states perfectly. That's the goal. Okay, this is the setup. And this machine, every second, you can use it every, let's say, so every use of that machine is 1 rupee. So every quantum state you prepare, you have to pay 1 rupee. Okay. And you are getting information at the rate of R bits per second. So, and say you can, for simplicity, you can use that machine every second. Use that machine every second. So every second you can set its lever position. It will prepare that quantum state and will throw it out. Okay. So what is happening? So just for simplicity, let's say R equal to 1/3. Okay. So so let's understand. So so you have after 3 seconds, right? You can either, so you can you have to decide what, and this entire apparatus and this whole, the state rho 0, rho 1, everything is known to Alice and Bob. The only thing that is not known to Bob is the actual realization of the information bits. Okay, is the setup clear? I just put a thumbs up if setup is clear.
So Bob just has to figure out what the sequence is given these qubits.
Correct. Given the
Okay.
quantum, yeah.
Okay.
Not necessarily qubits, but whatever states.
Yeah.
That's the setup. Is it okay? Yeah, cool.
Also, sir, this is the only aim that the Bob will have to recognize whatever Alice is want to send. That is the only aim. Nothing to do with the cost or reducing the cost or anything, overall cost.
Well, yeah, of course, everybody wants to reduce. Yeah, good question. So, no. So Bob wants to figure out the bits that Alice has encoded. See, it's every second these bits are randomly coming, and Bob has to figure out. But obviously, they want to reduce the cost. Otherwise, maybe it's not that hard, right? I don't know. Yeah, they want to do it at the least cost, because this is, see, what's happening is that every second they can use the machine, and every second they have to pay 1 rupee. So they want to reduce the number of the cost per second in some sense. So let me see. Oh, well, okay. No, I'll put it slightly differently. I'll do the setting slightly differently. I'll just tweak this a little bit. They have to use the machine every second, and every second they have to pay 1 rupee. Okay. The question is, what is the maximum rate at which they can communicate? So what is the maximum R at which they can afford to communicate? So at what highest information rate can Alice communicate to Bob? You can either look at it that way, or you can look at it as cost per bit. So either you can say, okay, I don't need to use the machine every second, but I want to reduce the cost per bit. Or you can say I want to maximize the rate. Is that okay?
Okay.
They're kind of similar. Let's for simplicity, let's do this. Let's say that every second they're allowed to use the machine and they have to pay 1 rupee. So 1 rupee is gone. No matter what they do, 1 rupee is gone. And they have to place the lever and it has to go. The higher the rate at which they can they can communicate, they get some rebate. You can think of it that way. So in some sense, their cost is say 1 minus R. So they want to maximize R. Somebody pays Alice and Bob for sending these R bits across. So every bit that they send across, somebody is going to pay them. So the net cost to Alice and Bob is 1 minus R, right?
So could you repeat the last part? Actually, there was some audio.
Yeah. So think of it like this. The setting is the following. Every second they can use this machine. They have to pay 1 rupee. And also one more thing I wanted to say, they want to ensure that Bob gets the bits with probability 10 power minus 27. That is, the probability that Bob gets the message incorrectly should be 10 power minus 27. So the probability that the Bob gets the bits incorrectly should be as low as 10 power minus 27. And so Alice and Bob is designing this protocol, and whoever is sending this green bits, right, they will give Alice and Bob, if they can send at R bits per second, they're going to pay R rupees per second to Alice and Bob. So the net cost that Alice and Bob is incurring is 1 minus R, because they're spending 1 on the machine and they're getting R rupees from the person who's giving these green bits. So their net expenditure is 1 minus R, and they want to minimize 1 minus R. So they want to maximize R. Is that okay? Okay. I mean, if there's any doubt, it'll get cleared as you go along. Don't worry. So just for simplicity, let's take R equal to 3. Okay, let's just take R equal to 3. Suppose somebody is sending at R equal to 3. Can we do it? Let's just see. Okay, so that means what? So after 3 seconds, right? After 3 seconds, they should have, suppose they are communicating 3 seconds at a time, right? They should, so in 3 seconds, Alice can choose to either prepare this or this, all the way until this. So she has 8 possibilities, and she has to essentially choose something for bit 0. So I'm going to write the bit 0, something for 0 and something for 1. Out of these, she has to pick something for 0 and something for 1, right? And this choice has to be communicated to Bob. And the moment she gets 0, she's going to choose that, and she's going to choose that combination on the machine, and that particular state goes to Bob, and Bob will do somehow trying to distinguish. So what she can do is she can decide what her x1 of 0, x2 of 0, x3 of 0. She can decide this, and she can decide x1 of 1, x2 of 1, and x3 of 1, right? And she will prepare this state if she observes the bit 0, and she will prepare this state if she observes the bit 1. This is, so she has to choose these two possibilities, right? And what you want these two to be distinguishable with a probability of 10 power minus 27. If we can do this, so if we can find three things, so possible, possible combination, it could be something like 0, 1, 1 and 1, 0, 0, right? This could be 1, 0, 0, this could be 0, 0, 0, 1, 1, which means that she would have prepared row 0 tensor row 1 tensor row 1, and this lady and the other combination would have been row 1 tensor row 0 tensor row 0, and these two states should be distinguishable with an error probability of at most 10 power minus 27. Is this correct? If I am able to communicate at rate 1/3 with just 1 second, yeah, with just one bit. Is this correct?
Yeah. Like why would you not choose row 0, 0, 0 and row 1, 1? They are like seems the
Yeah,
most distinguishable.
I'm just giving one possibility. So what they should do is they should, out of these 8 possibilities, they have to pull out two sequences, what we will henceforth call code words. They have to pull out 2 code words, and they have to decide on this. And for the 2 code words, they have to design measurements. So the measurement will be pi 0 and pi 1. And so that what you want, so if I call this gamma 0 and gamma 1, then pi trace gamma 1 row gamma 1 pi 0 plus trace gamma 0 pi 1/2 times this has to be less than equal to 10 power minus 27. Correct? This is the error probability. So half probability you will get bit 1, and in that case, what is the probability that Bob will get it wrong? Half probability you will get bit 0. In that case, what is the probability that Bob will get 1? That average has to be less than minus 10 power minus 27. Correct?
Yeah.
Okay. Any of you don't understand? Just tell me so that I'll go back. Okay. So let us. Is in general, this is not possible, right? Because if row 0, row 1 are not orthogonal, and there is no guarantee that row 0, row 1 are orthogonal, this is given by the system, right? In this case, this is not possible. There is no way, you will get it. It is not possible. If I choose something lower, it is possibly not possible to get such choices, right? So what do we do? Let's wait for a little longer period of time. So suppose I get n, let's say n seconds. I wait n seconds. How many bits do I get? I get n/3 bits, right? nr, which is equal to nr bits. So, which means I have 2 power nr possible bit patterns, possible information bit patterns. What are all the possible quantum states I can design, possible quantum states that can be prepared? Well, it is row 0 tensor row 0 all the way until row 0, row 0, row 1 tensor row 1 tensor all the way until row 1. Right, so this is 2 power n number of possibilities. Now r hopefully is less than 1, and what I should do out of this collection of 2 power n possibilities, I need to sieve out a collection of 2 power nr, right, such that they are distinguishable. So what does it mean? So choose what we will call code words. Okay. Xn of 1, which is essentially x1 of 1, x1 of, sorry, x2 of 1, an n length binary string for the bit combination 1. Similarly, an n length bit pattern for the message 2, x1 of 2, x2 of 2, xn of 2, all the way xn of 2 power nr. So what is this? This is x 2 power nr. Sorry. I have to find this, and a collection of measurements, not necessarily projective. So lambda 1, lambda 2 to lambda, so I'll say, and a POVM consisting of 2 power nr operators, lambda 1, lambda 2, lambda 2 power nr, that sum to identity, such that, so suppose, what is the probability I get a particular message? The probability I get a particular message is 1 by 2 power nr, because there are 2 power nr possibilities. Each bit can be of, with probability 1 by 2, it could be this or that. So if I choose a particular bit combination, this would what it would be, right? nr, because there are nr bits. So this is the probability that I get a particular bit. What is the probability of error? The probability of error is 1 minus trace of the corresponding m row x1 of m row xn of m, right? So take this whole operator. This is the probability of error corresponding to the message m. Now the average over all messages, this has to be less than 10 power minus 27, correct? Please indicate if you don't understand. I will explain this. So what do I need? If I have to be able to communicate at rate r, that means I have to design 2 power nr bit patterns. I have to identify 2 power nr bit patterns among the total number of 2 power n patterns. And for each pattern, I have to design a POVM operator. So that means the sum of those POVM operators is identity. And the probability of error. So what is the probability of error if I send the message little m? That is this, because this is the probability that Bob will decode correctly. So Alice has prepared the quantum state corresponding to the message m, and Bob gets the outcome corresponding to the operator m, and 1 minus that is the probability of error, and then I average over all the messages. That average has to be less than 10 power minus 27. So if I will be able to communicate at rate r, I should have all this ingredients. So I should have a bunch of code words, and I should have a collection of POVM that satisfies this. If I can do that, then I'm able to communicate at rate r, and I want to find the maximum r at which I can design this. This is very important. So if you don't understand, ask me to stop, and I will explain this once again.
Sir, can you repeat once again?
Yeah, sure. So where did you lose? Okay, so let's see. Let me go one step slower. So let's take r equal to 1 by 3. Let's take 3 seconds. So Alice could have got either this or this, right? And what Alice should do, Alice in 3 seconds, she could have prepared, she could choose any one of, she could have prepared any one of these states. And what she should do is she should assign something for 0, right? So it could be, let's say it could be 0 tensor row 1 tensor row 1, and for this it could be say row 1 tensor row 0 tensor row 0, right? So this, I call this 0 1 1, I am calling x1 of 0, x2 of 0, x3 of 0. So this is the message, and this is the length, this is the index of the sequence, index of the bit in the sequence, in that index of the bit in that pattern. Okay, and this is x1 of 1, because the message is 0, message is 1. Okay, so x2 of 1 and x3 of 1. Now, so the thing is that it is not in general possible to identify 2 states out of these 8 states that are distinguishable with probability of error at most 10 power minus 27. So what do? We wait for a little longer period of time. So let's say we wait for 45 seconds. If we wait for 45 seconds, all the possible, the number of bit possible information bit combinations which she has to design quantum states for are 2 power 15, right?
Yes.
Because you're so every 3 seconds you're getting 1 bit, so you ended up getting 15 bits, and those 15 bits could be any one of these 2 power 15 combinations. What are all the states she could have prepared? Well, she could have prepared any one of the following states, right? So remember, it's 45 seconds, so this is of length 45. She could have prepared any one of these possibilities, and what she should do, she should choose one possibility for this, one possibility for this, one possibility for this, and so on, and that thing has to be communicated. So let's say for the bit pattern 0 0 0 0 0, she will prepare, let's say she will choose the state row, I'll call it row x1 of 0. So x1 of 0 tensor row x2 of 0, 45 of 0. Do you agree with this? Something.
Yes.
So this is your choice. So your choice is determined by this sequence, right? Similarly, so she has to choose 2 power 15. Actually, I mean 2 power 15 minus 1, because I've added the 0 also. So x45 of 2 power 15. Do you agree?
Yes.
Okay. And not just that, for each one of this, Bob has to, I mean, they have to also come up with an operator, lambda 0, all the way until lambda 2 power 15, so that if I do the trace of row x1 of m, row x45 of m times lambda m, this has to be, this is the probability of correct detection. If I do this and I average over all the messages m, right, with 1 by 2 power nr, right, 1 by 2 power 2 power 15, this has to be less than 10 power minus 27. Do you understand this expression?
Yes. Yes.
Okay. So what do I need? If I'm able to communicate at rate r, what does it mean? I have to choose out of all the possible 0 power 1 to the power n. There are 2 power n possibilities here. Out of these, I have to choose 2 power nr, what we call code words, that are patterns. So those, so I denote them as those code words, I denote them. So it's a table, right? It's a table. What is the width of that table? So I'm putting message one, 2 all the way until 2 power nr here. So this is like 2 power 15. And this is n. So there is a bit combination here. There is a bit combination here. So if she gets a particular, say, 23, if she gets the bit combination corresponding to message 23, she will take this table. So there will be a bunch of 0 1s in this table, and she will place the lever of that machine in that state. Do you agree?
Yes, sir, even though so you said R is 1/3, right? So in 3 seconds we get 1 bit, but
Correct.
the machine will be producing the qubit every second. The density operator rho x, it will be producing every second.
Yeah, in some sense you should look at it. It's like, okay, that's a good question. So let's say she waits for 45 seconds, and she can at once decide the 45 positions of the lever. Let's say
Okay.
it's not that, if you don't use it the second, it's kind of gone. Yeah, that's a good question. That's a good point, but just for, it's kind of a technical thing. So you wait 45 seconds, and at the end of 45 seconds you can place 45 choices. Is that okay?
Yes, sir. Okay.
Okay, so now does the whole thing make sense, the code word and the POVM?
Yes, sir.
Clear to everybody? Just put a thumbs up. I mean, just because I want you to understand this, and I will actually write formal definitions for this, and then I will prove the make the theorem statement. So I will just formalize all of this. So consider what we refer to this row x's, right? These so what we had is row 0 and row 1, right? So this collection, so consider, we call it a classical quantum channel, and you will see why we call it that way. Consider a classical quantum channel characterized, it's exactly the same, you don't have to worry about what I'm saying here, characterized through the collection rho x belonging to D of h, x belonging to x. So in some sense, what is happening, what do I mean by a channel? This whole process, right? So what I mean is this whole box is kind of thought of as a channel. So you can only choose the levers here, the location of the levers. So once you choose the location, the quantum state comes out. So this entire transition from your lever selection to the quantum state coming out is just called a CQ channel. But it will become clear as we go along. You don't have to essentially you don't have to worry about it. Essentially, think of what I said so far. Consider a CQ channel characterized through the collection rho x. I'll give you a couple of definitions. So definition 1.
So just one question.
Yeah.
So X was just 0, 1, right? In the previous example.
Yeah, correct. In the previous example,
Okay.
X was the 0, 1. Yeah. So, and so whatever I refer to as a code word and a measurement, right? I will just formalize that. And n, comma r, e, comma lambda, code, quantum code, consists of 1 for the CQ channel rho x, this collection rho x consists of exactly the elements that I mentioned. So 1, a collection of 2 power n r, what we refer to as code words. So I will explicitly say what that is. So xn of 1, which is essentially x1 of 1, xn of 1. So xn, so for each possible bit combination, there are 2 power n r bit combinations. For each possible bit combination, I have a pattern of locations for the lever. That's really what I mean. So a collection of 2 power n r code words where each of these elements, right? These are essentially choices in X, right? So each xi of m, right? So then let me go back to blank. Xi of m belongs to X for every 1 I n and m equal to 1 to 2 power n r. So it consists of a collection of, so these are, so if I see the message m, so Alice will put the machine in the location x1 of m, x2 of m, x3 of m to xn of m. And 2, given the quantum state, a POVM lambda equal to lambda 1, lambda 2 power n r, consisting of two power n r positive semi-definite operators. That sum to I tensor n. So that is what is a core. Okay. So this collection, generally this collection, right? Xn of 1 all the way until xn of 2 power n r. This is referred to as a code book, or people ignore the book and just say this is a code. Essentially, it's a choice of patterns within from xn. Okay. Why do I? So if you see my definition, I have an E here sitting here. Really, all that I mean is that E is like the encoding. Okay, it's called the encoding because Alice encodes the bit pattern into a choice of the position of the levers. So this E is essentially a map from 2 power n r to xn, right? And the message m goes to xm of 1 all the way until xm of 2 power, sorry. The subscript is the location of the bit, the xn of m. Okay, so I'm just calling it E, just encapsulating the entire code word as as a function from the message set to the sequences. So this is my code. So I will write 3 definitions and then I will clarify if you have any questions. So definition 2, consider, I know it's 8:46, I'll just take 5 minutes and I'll end, okay? Consider the code n r e lambda designed for the CQ channel rho x where xn of m is E of m. So I'm just writing down what I stated in the previous case. So this is also, I'm going to just write x1 of m all the way until xn of m. This is my code. The average probability of error of the code is exactly what I told you before. So it is 1 by average. So the probability that you will get message m is 1 by 2 power n r. And in that case, the probability that you will make an error is 1 minus trace of lambda m times because Alice has prepared this quantum state. We have all agreed on this code, and you do the you make the measurement with the POVM, and you happen to get an outcome corresponding to a different operator, not the one that she actually designed for you. And when I sum over this over all m equal to 1 to 2 power n r, this is the average probability of error, and I will denote this as epsilon. I don't know what is this, epsilon or xi, I don't know. E comma lambda, because E is there in the choice of the code words and lambda is there in the choice of the POVM. So that's why I call it E of xi of E comma lambda. So what have I done? I have defined a code. I have defined an average error probability of that code. Okay. And definition, a rate r greater than 0 is said to be achievable. So I can, you can say I can communicate at that rate if for every epsilon, so no matter how small an error probability I seek, there exists n some index such that for all n greater than equal to n epsilon. So if I choose, instead of 45, I had gone to 450 or say 3 million, I could have got my probability of error down to 0. That's what I mean. There exists an n epsilon such that for all n greater than n epsilon, there exists a code, a CQ code n r e, obviously it's a function of n, and lambda n with error probability xi of en comma lambda n is less than equal to epsilon. Okay, so I wouldn't be, don't be worried if you don't understand the last definition, and if you have understood the first two definitions, that's good enough. But I'll just keep this here and ask me any questions here, and then I'll also push the thing a little bit and then ask you if there you have any questions with the next. Is the definition 1 clear? And put a thumbs up if it's clear. Okay. Is definition 2 clear? Remove that and then again. If you don't, just put a thumbs down or something. And I'll come back to it next time. And definition 3 in my guess will be slightly complicated to understand, but but I will explain this, and this is and this whole thing. Okay, I will quickly tell you what is happening. See, you had you could have. So what are we doing? So you could have prepared any one of these states, right? So I'll very quickly, I mean, just 3 minutes. So you could have prepared any one of these states, right? So I equal to 1 through n. You take any combination xn belonging to xn, you could have prepared any one of these states, right? But the problem is, remember, two states are distinguishable if and only if they have orthogonal support, right? So what you are trying to do, you are trying to pull out a bunch of states. So I'll call it xn of 1. So what I mean by this is x1 of 1, xn of 1, sorry, yeah, xn of 1. You're trying to prepare a bunch of states that are in some sense asymptotically orthogonal so that you can distinguish them. And the question is, how many such orthogonal states can you pull out of these all possibilities? Okay, so you're trying to identify these states out of these states that are in some sense asymptotically, as n becomes large and large, they are asymptotically orthogonal so that I can distinguish them. Remember, the two states are distinguishable if and only if they're orthogonal. So you're trying to, so you have a big space and you're trying to pack orthogonal subspaces essentially. That's really what you're doing. So that's why it's called the packing lemma. So we'll actually come to that in the next. So I will motivate this and tell you, what kind of we're after, and we'll go to the packing lemma, and then we'll do the, we'll use the conditional quantum typicality. So that's the direction we are going. I will explain the last definition. Yeah, question. Yeah, please. Saptarishi, you have a question?
Yeah, sir.
Yeah.
Sir, which part should I refer this in the will?
Yeah, this is slightly, I'm doing it slightly differently from Wild, but this is essentially in chapter 20. See, Wild gives a different motivation for the packing lemma, and that's not, I don't know if that is very convincing. The actual use of the packing lemma is really in this problem. So I am slightly doing it mixing 16 and 20.
16
So
and
you can look at 20.2.1, but he does it in a slightly more general setting. And you can also read the introduction to the packing lemma. Essentially, I'm mixing the two.
Okay.
Yeah.
Okay. Sir, do you have 5 minutes?
I can have a discussion session on this whole thing. Last 2-3 classes, I can have a discussion session tomorrow evening or something. We can. Yeah.
No, I have some things to ask you. Is the class over, or are you going?
You have to go to the mess. So if you want, we can meet later.
No, just 2 minutes. I'll just ask you.
Yeah. Go ahead.
It's not related to this. I just asked about the summer.
No. Then we'll meet little later.
When?
Wait. First, let me. I want to put this class thing. So first, let me